Hello everyone, today we will be looking at the basic, yet one of the foundational algorithm for machine learning. This will give you an intuition about how machine learns and improves. Let's start with the most fundamental algorithm, linear regression. Linear regression is a type of supervised machine learning algorithm that computes the linear relationship between the dependent variable and one or more independent features by fitting a linear equation to observed data. Let's try to understand this definition. Linear regression comes under supervised learning, where we have input and output features. We can have one or more input features which are independent to each other, and one or more output features which are linearly dependent on inputs. For better understanding, let's consider an example. We are given this ideal data with no outliers. As input features, we have area of a plot, and our outputs are the prices. Intuitively, we know they have linear relationship between each other, but it's a challenge for a computer to understand the pattern beneath this data. To begin, let's plot this data. We can clearly fit a line which represents the scatter plot. As a human, we can easily predict the price of a plot of area 120 meter square or say 150. It's easy because by looking at a scatter plot, we got to know the coordinates of each point at once, and we plotted an imaginary line to represent the solution. But for computers, we need to rely on mathematics. Let's refresh our good memories of mathematics class. We know a line can be represented by this equation, which is slope-intercept form of a line. Here, m is the slope which tells us the inclination of the line. To calculate m, we use this simple formula, where theta is the angle subtended by the line on x-axis. By changing this theta, we can change the inclination of the line. Notice it covers the whole 2D plane. But this alone can't represent every possible line. That's why here comes our little c. This represents the point where the line intersects y-axis. If we imagine a line passing through origin, then its y-intercept or c is 0. And if we change this value, notice how the line glides over y-axis. Utilizing these two parameters, we can represent any line on the 2D plane. Same concept can be used to solve multi-feature problems where we have more than one independent variables. Here, as a solution, we don't get just a line, but a hyperplane which best fits our multidimensional space. We have enough basics to move on and understand how machine learns this intuitive yet complex problem. At first, with no knowledge of data points, a line is drawn at random, and using a loss function we calculate the error. And this process is done iteratively till we minimize our error. When we get the least possible error, this means we have got our best fit line. But what is this loss function? Well, it is the function of distance between these points and the line. This little square is just to exaggerate even the slightest distance, so that our machine tries to compensate this error. After adding square distances, we get our cost function. But how a machine knows which line will produce the minimum cost, or to rephrase it, what values of m and c will produce the least cost? We can't perform iteration indefinitely because it's computationally exhaustive and sometimes impractical for multi-dimensional problems. To tackle this issue, we use a famous technique called gradient descent. Looking at the formula, we can say error is the function of m and c, because they are the only changeable parameters. If we represent this function on a graph, then it will look something like this, where x and y represents our m and c, and z represents our error. These highs represent the maximum error, and these troughs represents the least error. So instead of iteratively computing values of m and c, our machine takes a walk on this landscape. By the way, this landscape is plotted using a beautiful method called partial derivatives, which calculates the rate change of error function with respect to m and c. Coming back, our machine slightly changes the value of m and c and realizes where it needs to move. And it tries to find the path downhill, where the best value of m and c lies. But it has to face many challenges. What if the direction it is moving is local minima and not global minima? Or what if it takes bigger steps and overshoots our optimum point? Or takes very small steps and never reaches the minima? To deal with this problem, we need to initialize the learning rate, which is nothing but the length of each step it is taking on the landscape. We need to experiment with this value to find our global minima, a number not too small, not too big. And that's it. Our machine now knows how to plot the best fit line. Also, This creates foundation to many complex machine learning algorithms. I know the concept behind it was not intuitive at all, but we don't have to do all these complex calculations ourselves. There is a Python library which does all the heavy lifting for us. Here is a simple code which implements linear regression in few lines. You can experiment by changing values in x and y and plot the solution given by the algorithm. That's it for the video. Now you have entered into the world of machine learning. Best of luck and I'll see you in the next one.